Okay, so in module 1, we went over many integration techniques. We looked at inverse functions that taught us how to understand that the log and the exponential were inverse functions. We talked about how to take the derivative of those, talked about taking integrals of those, talked about functions that when you integrate them involve exponentials or logs. We looked at L'Hopital's rule. We looked at U substitution, which was a review, but I think some of you still need practice on that. We also looked at integrals that result in inverse trig functions because we went over the derivatives of inverse trig functions. So all of that you will see again, but this module is completely different. Okay, so this module is going to be looking at how we can determine volumes, all right, by slicing, volumes by revolution in a disk, and volumes by washer. So this is what we're going to be doing. So first objective, to determine the volume of a solid by integrating a cross section. That's the slicing method. To determine the volume of a solid by revolution using the disk method, and to determine the volume of a solid of revolution that has some open space, and we're going to use the washer method. Okay, so if you take it, so let's say I'm gonna grab something off my desk here, and it happens to be this little tiny notebook. Okay, so I take this little tiny notebook and I take only one sheet of this little tiny notebook. This one sheet is actually rather thin, but this one sheet has area. So I can look at the base, or the length times the height. Okay, so the length times the height gives me this area of this little sheet. And it's just very thin, has no volume whatsoever. It's just a thin sheet of paper. It's two-dimensional. But when I start to stack up a bunch of them, so now if I stack up a bunch of these little sheets, I end up getting volume. So now I can say that this book has a length, it has a very skinny width, but at least it has the width, and it has a height. Okay, so what we're going to be doing is we're going to be finding volume. Okay, and our volume is going to be integrating or stacking up the sum of areas. So when you stack up the sum of areas, like a loaf of bread, each time you take a loaf of bread and you add it to the slice of bread, and you add it to the next one, you end up with a volume or a loaf of bread. If they were infinitely many slices, we would be able to compute this using the integral. Okay, so I'm going to grab a picture from over here. First, I'm going to grab this integral here. And so what we're going to be able to do is do our volume is going to be the integral of A to B. That's wherever we're integrating from, our length. And then our area is going to be sticking up outside of this length, okay? And we also will be doing that by the Y value. So we will also have this value. Okay. All righty. So we have these two volumes, and these are the formulas that we are going to use. Okay, so my first picture, I've already drawn it, but let me see, grab volume by slicing. Okay, so the first thing we're going to do is volume by slicing. And like I said, that's like looking at a loaf of bread, and we have each individual slice, and when we stack it up, we get this nice fat volume of bread. Okay, so here we have, I'm going to take and grab my picture. Yes. Hello. So, somebody have a question? All right, I really don't want to draw this picture again, but I'm going to. Okay, so what's the volume by slicing? All right, so let's say I have Why did I go too far? There we go. Okay, so on the ground, I'm going to have some base. Okay, whatever the base looks like. So let's say the base here is just a very simple rectangle. Okay, so on the ground, I have a rectangle that looks like this. Okay, so this is my base. All right, so my base here, as you can see, here's my base, and it goes from some A is here, up to some B. Okay, so this is my base. And this right here is some function y of x. Okay, it could be a line, could be a circle, could be a semicircle, it could be a triangle, it could be anything. Okay. All right, so what I want to do now is I want to say that, so this is the base. The base is governed by this area here. And now what I want to do is I want to take a cross-sectional slice. So my cross-sectional slice, I'm going to make it another color. My cross-sectional slice is going to be some rectangle that fits just ever so slightly like that. So there, this rectangle has an area. So that has an area, which I'm going to call A of X. And that area, if I stack a bunch of them, that area will go all the way from A, and then that area can move that area can come all the way down here. I'm going to have a ton of them. So as you can see, there's the area. All right, so here's yet another area. So if I had infinitely many areas, then I would be able to say that the volume of the solid made by adding up these slices, the volume of the solid created by laying these slices side by side side by side would be the volume. It's going to be the integral from A to B. And I need to know what the area is dx. Well, how would I find the area of this piece? All right, so the area of this piece is simply going to be this length, which for me would be y of x, times the height, which somebody would have to give you. So the area, if we pulled one of these out, if I pulled one of those out and just set it right here for a moment. Okay, so that's my slice. So here's my slice. You can see from here that this distance is just y of x, and this distance would have to be given or found. Okay, I see I have 2 people in the chat. Okay. All righty. Any questions? All right, so our first problem is going to be one just like that. First, I want to give you the steps for solving one of these problems. Okay, so the steps for volume by slicing. The first thing is draw the picture. All right, draw the solid. It's harder to do this if you don't have at least some kind of a sketch so you know what it is that you're working with. Identify the limits of integration. That is, see how it starts at A and it's going all the way to B. If that was -2 and B was 2, I would know that it starts at -2 and goes all the way to 2. So wherever I'm going to start my slices, all the way up to where I end my slices. That's my limits of integration. Then identify the cross-sectional area. So I know the area of this is y of x times whatever height that is. I don't know what that height is right now. Right. But somebody would give me an idea of the area, how to find the area of this slice. And then I would just integrate it from A to B. So once I identify the cross-sectional area, I find a formula for it. So the formula for this one would be h of x times y of x. And then substitute a of x into the integral and compute the integral. Okay, so I guess I should add one more on here, which would be compute the resulting integral. Okay. All right, so that's the technique, all right, that we're going to use. First, we're going to draw it, identify the limits of integration, identify the cross-sectional area, find a formula for it in terms of x, substitute a of x into the integral, and then compute it. Okay, all right, so our first problem . Okay.
Can you go back up a little bit so I can see step 5?
I certainly can. Okay. So in example 1, we're going to consider the solid whose base is bounded by the upper semicircle x squared plus y squared is equal to 4. So I'm not going, and I read the whole problem, but I could tell you guys, always read the whole problem at least twice, kind of get an idea what the important words are. Semicircle, x squared, I got an equilateral triangle. That means I'm going to need to find the area of that thing. So there are many things that we have to work through in order to solve this problem. Okay, so let's draw this. And again, my father was an architect in his early career, and he could draw like nobody's business. I don't have that talent. Okay, I am not, I don't draw very well. I'm gonna do the very best I can. Okay, so I need a semicircle. So let's grab this and see if we can put some kind of circle in here. Again, not real good. Oh, that's not bad. Okay, so I'm going to get rid of what I don't need because the semicircle is bounded the upper semicircle, so I don't need the bottom part. So I don't need this. And I don't need this. And I don't need this. Okay, so I need the semicircle. There we go. That is bounded. So this semicircle is x squared plus y squared. So x squared plus y squared is equal to 4. Now, as you can see, this is z. All right. This is y. And this is x. So if this were actually drawn over here, it would be a semicircle. And this would be my semicircle. So I wouldn't need any of that. Okay, so as you can see now, here's the y-axis and here's the x-axis. And z would be sticking straight up in the air. Okay, so what I care about right now is this semicircle, this region right here, is the base of my solid. So it's the base. All right, now it tells you that's the base. So that means, and the cross-sectional areas are equilateral triangles. All righty, that's not so easy to draw, but they're equilateral triangles. So they are equilateral triangles and they are standing up in the air. As such. So this is the equilateral triangle and they are standing up in the air. And there's actually more of them. So if I were to draw another one, there's a bunch of them and they're all standing up in the air. And this is making my solid. Okay, so as you can see, that's my equilateral triangles. All right. So as you can see, these are the equilateral triangles and there's a solid that's very pointy at the top. Okay, because it's made with these triangles. And the bottom is very rounded and nice because it's inside the semicircle. Okay, so each base of the equilateral triangle, that's the base right here, is literally standing just like this in the XY plane. So note that the triangle is actually standing up off the page. Okay, so this is the base of the equilateral triangle. So what I need to do is we need to now find the area of the equilateral triangle. Okay, so let's go back to our steps. Our first step, we drew it. We drew the solid. Our limits of integration. Okay, well, let's see. Where are we going to go? So this triangle starts way back here at this point, right there. And then the triangles go all the way up to this point right there. Okay, so let's find the limits of integration before we find the area of the equilateral triangle. I need to do that. All right, so let's find the limits of integration. Okay, well, our triangles start at that point right there, but that's this point right here. And our triangles end right here. Okay, so what is that point? Well, our equation y is the square root of 4 minus x squared. And at that point right here, y is equal to 0. So we have x squared is equal to 4. So x is equal to positive and negative 2. So now I know this value starts at negative 2 and it ends at 2. So those are my limits of integration. So I already know then. So I go from negative 2 to 2. So my integral is going to look like negative 2 to 2 of some area of x dx. So what I have to now find is the area. Okay, so we've identified our cross-sectional area. All right, so our cross-sectional area is this. The cross-sectional area is this triangle. All right, so we need to find the area. All right, so the cross-sectional area is an equilateral triangle. So now we need to find the area, find that. Yeah, a lot of people, oh boy, that Del State's internet is bad today. It is hurting some people. Okay, I'm sorry. It was glitchy yesterday too. Okay, so the limits of integration. All right, so this, we drew the solid. This was 2. This was 3. And now we're at 4, finding the area of the equilateral triangle. Okay, so we have an equilateral triangle. What's its base? Its base of the triangle. Well, first off, the area of any triangle is what? What's the area of a triangle?
Half base times height.
Okay, 1/2 base times the height. Okay, so for this triangle, its base is this line that has height for any given x. Its height is the square root of 4 minus x squared. Okay, so for this triangle, given any x, the base is equal to the square root of 4 minus x squared. Now, we have an equilateral triangle. We have to find its height. How do I find the height of this equilateral triangle? Whoops, get that back. We're going to use Pythagorean's theorem. Okay, so when we drop a perpendicular, first off, we know what this side is. This whole side is B. And it's an equilateral triangle, so this side is B. Okay, and here is H. All right, so we know that A squared plus B squared equals C squared for Pythagorean's theorem. So here we're going to take this side is going to be this piece is 1/2 of B. So we're going to get 1/2 of B squared plus H squared is going to give us B squared. So therefore, we're going to get 1/4 B squared plus H squared is equal to B squared. All right. I don't like that, but the fact that I put that Pythagorean theorem there, let me get rid of that because I don't want you to confuse A and B. Okay. So that says H squared is equal to 3/4 B squared. So now we know H is the square root of 3/2 times B. All right, so now we know the height. Again, this is the same triangle. This is that same yellow triangle. Okay, so now what is B? H then is equal to the square root of 3/2. And we said B was the square root of 4 minus x squared. So now we know the height. Okay. So therefore, we now know what A of x is. A of x is 1/2 the base, which is the square root of 4 minus x squared, times the height, which is the square root of 3/2, the square root of 4 minus x squared. So therefore, we get the area turns out to be the square root of 3/4. And then this just gives us 4 minus x squared. So we now know the area of the triangle. All righty. So therefore, this is part 5. 5 says find the area, find A of x. So this was 5. And then 6 says compute the integral. So now I'm going to have the integral from -2 to 2 of the square root of 3/4 times 4 minus x squared. This is an easy integral. I can pull out the square root of 3/4 and integrate, and I get 4x minus 1/3 x cubed. And that gets evaluated between -2 and 2. And that answer turns out to be 8 the square root of 3/3. Okay. Questions, explanations, confusions. Where did I get X? Where did I get B? Where did I get? Everybody good, or we have questions?
Yeah, I'm good. It's just like a lot to like.
Oh, this chapter, this module is a lot. This module's thick, okay? I'm telling you now, this module's thick. And this is just the first kind of problem we can do for the volume. It is a lot, okay? So one of the things you need for this problem is stick-to-itiveness. You need to stick with the problem. If you don't stick with the problem, you're not going to finish it. Okay. All right, here's example 2. Okay, so example 2 is a little nicer. All right. Okay, so here's example 2. The base of a solid is bounded by the curve y equals the square root of x and the line x equals 4. The cross sections perpendicular to the x-axis are squares. Find the volume of the solid. Okay, so as we read it again, it says, the base of a solid is bounded by the curve y is equal to x square root of x and the line x equals 4. So let's just draw that for a moment, not even in 3D. Let's draw that in 2D. Okay, so I know I don't need this half. Okay. All righty. So the line y is equal to the square root of x looks like this. And the line x equals 4 looks like this. So this is the base. So that's the base of my solid. Okay, I can see that I'm starting here at 0. So I've drawn the picture. I can see that I'm going to start here at x equals 0 and go all the way up to x equals 4. So in number 2, my limits of integration are from 0 to 4. So I know I'm going to have the integral from 0 to 4. When I find it, it's going to be a of x dx. Okay, this one's actually a really easy one. The other one I just did, I started with a hard problem and then came to an easy one. Okay, it tells you that the cross sections perpendicular to the x-axis are squares. Okay, so first thing, where's perpendicular to the x-axis? So perpendicular to the x-axis is in this direction. Okay, and it says the cross-sectional areas are squares. Okay, so that means sticking up in the air are squares. Okay, so there are squares, and imagine you have to think this thing is sticking up in the air. All right, it's actually making a 45-degree angle with this ground. So the area that I'm looking at are squares, and they're sticking up in the air. if I were to draw this in 3D, I would have something that looks like this. I have y is equal to the square root of x would be coming around like this. And then that's what, and here is the line x equals 4. So now you see my base, and then sticking up out of that are squares. It won't. Here we go. It don't look like a square yet, but it will be in a minute. Aha. Okay, so sticking up in the air are squares. So there's my area sticking up in the air. Okay, so I now know that my cross-sectional areas are squares. Did I skip something? I identified the cross-sectional area. All right, so those things are squares. And so I need to find the area of a square. Okay, so that's not too hard. If I have a square, a simple square like this, what's its area? What's the area of the square? Hello.
All right. Base times height.
Okay, and are they, and the base and the height are the same, correct? So for the,
Yeah.
yeah, thank you, Jadeja. Okay, so for the area of the square, the base and the height are the same. Okay, so basically what that means for me is I need to figure out the base. Now the base is what's laying on the ground cross-sectional to X. Here's the base laying on the ground cross-sectional to X. Okay, so therefore this is the base. So if I go back to the picture, the base is simply this height or this value, which is y. And y is the square root of x. So the base y, this side is the square root of x. Okay, so therefore the area is going to be the square root of x times the square root of x. And that's just x. So now I know a of x. So now 6, I compute v, the integral from 0 to 4 of a of x dx. That's the integral from 0 to 4 of x dx. And then that thing is, which is so simple, just comes out to be 8. Okay. Any questions about that? So the hard part is to figure out where the cross-sectional area is. And remember that your slices are standing up like this. Your slices are always up in the air. So the ground is flat, X and Y, and then you're stacking slices, and you're stacking slices on top of your base. And you have to remember when it says perpendicular or parallel, which direction that they're in. Okay. All right. Okay, I'll do that other example tomorrow. Now, a lot of people like this one because this is the easiest one of all. Whoa. And that is volume by discs. Okay. So the interesting thing about volume by disc, imagine, oh, I'll be right back. They're not flat, but they'll work. Okay, here's a disc. All right, it happens to be a coaster. Now, if by chance you take, and this is my cross-sectional area, what is the area of this? Can y'all not see me? What is the volume of this disc? What's the volume of a circle? I'm sorry, I'm saying volume. What's the area of a circle? What's the area of this disc? All right, somebody typed it in. What's the area of this disc? Pi, good, thank you. Pi, I'm sorry, I was saying volume. The area of this disc is pi r squared. Okay, so when we use the disc method, the area is going to always be a disc. So therefore, the area will always be pi times the radius squared. All right. So now the difficulty for these types of problems is to identify the radius. And you will find that these are much easier than the last, and you will like these problems. You're going to want to do every problem this way. You're going to be like, why can't we use the disc method? Okay, so this is how this works. We are going to revolve a solid region about an axis. Okay, so we're going to revolve a solid region about an axis. And when you do so, the cross-sectional area will be a disc. Okay, so here's an example.
No, we're supposed to skip on the just okay. I think there's no.
Okay, so let's say we have this region. Here's some function f of x. Y is equal to f of x. And it goes, let's say, between here and here. If I revolve this region, so what I'm going to do is I'm going to take an area, something like this notebook that's flat. And I'm going to sweep the whole area out, revolving it about an axis and bring it back. I'm going to have a solid. Okay, so again, I'm going to start with this area. I'm going to sweep it out. So I'm going like this all the way around. And as I'm doing this, you guys should be able to visualize the solid it just created. Okay, so that's what I'm going to do. So down here, I'm going to have a similar curve, but I am sweeping this thing out. So when I sweep it out, when I revolve this around like that, I get a disc. When I revolve this around here, I get a disc. So for any x, here's an x. I'm going to take that point. I'm going to revolve it all the way around the axis. And I'm going to get a cross-sectional area that looks like this. So now notice my cross-sectional area is a disc. And that disc has to start down here at x equal to a, and it has to, and it goes all the way up to here where x is equal to b. So I can easily see that my volume is the integral from a to b of my area. But the difference is my area is a disk. What's its radius? Well, that's the interesting part. The radius is just this height. So there's the radius. So for any given x, I have a circle. So here's my gray circle. That's the circle. Here's the cross-sectional area. And there's some radius right here. But this point is on this curve. So therefore this height is y of x. So now we get, for this problem, the radius is y of x. So our volume, our area is pi times whatever the radius we find squared. And in this problem, it happens to be y. So therefore, for the disk method, you get the volume is the integral from a to b of pi times whatever radius you find squared dx. Okay, so this is the volume of revolution about the x-axis of a region bounded by y is equal to r of x on the interval AB. All right, so this one is a little bit more fun. All right, so here's our first problem. Okay. The region bounded between the curve y equals square root of x and from 0 to 4. And the x-axis is revolved about the x-axis to generate a solid. Find the volume of the solid. Okay, so we already drew that, but I can draw it again. So I have okay. I actually don't even need that. Let me just do it this way. Okay, so let's draw it. Here's y equals the square root of x. That's the function again. We had x equals 4. So here's my region. So that's my region R right there, my region. So I'm going to now revolve this about the x-axis. So when I revolve it about the x-axis, I get something that is a solid so for any given point, let's choose this point X, go up to the curve, and then revolve it around. Okay, I pushed the button I wasn't supposed to. Let's go up to the curve and revolve it around. And there's my disk. So as you can see, my cross-sectional area is a disk again. And that disk, so my three-dimensional figure kind of looks like if you chopped off a football, if a football were full of cement and then you chopped it in half, you would get that 1/2. Okay, so you have 1/2 of a football, but it's filled because this whole thing was filled. And when I flipped it all the way around, I got a solid. So this is my area. So I need my area. I already know, wrong color. I already know my area is pi times whatever the radius of this thing is. So as I can see, the radius is just this height. And this is y is equal to the square root of x. So whatever x is, this height is the square root of x. Okay, so therefore my volume, the integral, well, we already said we're starting at 0 and ending at 4. So we did that. Those are our limits of integration. We already know our cross-sectional area are disks. And so therefore we know this is the integral from 0 to 4. Our cross-sectional area is pi times r of x quantity squared dx. But that's the integral from 0 to 4. of pi. R is just the square root of x, quantity squared dx. So you get pi times the integral from 0 to 4 of x dx. And this gives you 8 pi. So that took the region, the original region, revolved it around the x-axis. So it kind of opened up like an accordion. So it started like this, and then it revolved all the way around and came back. And the cross-sectional areas are these little discs. If I were to slice it, I would see circles, slice, circles, slice, disc, slice, circles. Okay. Any questions about that? You have to make sure you see the disc. So you need to draw the picture so you can see the disc. Okay. Okay, so here's example 2. We want to find the volume of the solid generated by revolving the region bounded by the square root of x and the lines x equals 1 and x equals 4 about the line y equals 1. We got to draw that thing. Okay, so I'm gonna let you get a minute to write it down. Okay. So I want you guys to attempt to draw the region before I do. So you know you have to draw the curve y is equal to square root of x. We've used that curve several times. So hopefully by now you know which one that is. The line x equals 1, we know what that is. The line x equals 4, we know what that looks like. And about the line y equals 1. Okay, so this one's a little trickier. All right. Okay. So y equals square root of x goes like this. All right, so that's the first thing. Line x equals 1. So x equals 1 looks like this. And then x equals 4 looks like this. And then I'm revolving this region about the line y is equal to 1. Okay, so that turns out to be this small little region right here. So that's the region that I'm going to revolve about the axis. All right, so that's my region. We already know this is y is equal to the square root of x. We already know this is the line y is equal to 1. Okay, so now that says for any x, so let's find the x. So this is x is equal to 1, and this is x is equal to 4. So our limits of integration are always already going to be the integral from 1 to 4. Okay, so now we're going to pick an X. I like that X right there. I'm going to go up. I'm going to take that point, and for that X, I'm going to revolve the region about a circle. And by golly, I get this is my region R, my region A. So that's my disk. So now that I see my disk, remember, you have to draw it and see your disk. So you could, that's the only way you're going to find the area of your disk. Okay, so now that I see my disk, I need to compute its area. And at this point X, I need to find out what the radius is. So here is the radius. So the radius of this disk is here. That's the radius of the disk. So for any value of X, that's its radius. So therefore its radius is only this length. It is only this piece. So now going from the ground, going from at y equals 0, all the way up to the top is the square root of X. So that's the length of the square root of X. But I have to subtract off going from 0 to 1. So that's the -1. So now I know the radius of my circle. That's its radius. Okay, so I'm ready. I know the volume is equal to the integral from 1 to 4 of pi. Its radius is the square root of X minus 1 quantity squared dx. Okay. And if I compute that integral, I just get 7 pi over 6. All right, any questions about that? So those are revolutions about the x-axis. All right, how about revolution about the y-axis? Okay, so you can take any region say whatever the region is. And I can decide that from a certain value of y to another value of y, so from C to D, I want to revolve it. So when I revolve it, I end up with something. Why did I draw such a cookie curve? Okay, so when I revolve it, I'm going to now choose a y, find its value, and revolve it. Once again, you can see the disk. But this time its radius is going to be a function of y. Okay, so it's radius. So now I'm going to write this curve as x is equal to g of y. And then I go from C to D. And so my radius is now going to be a function of y. So it's going to be a function of y. Okay. So therefore, if I revolve around the y-axis, I get the volume is the integral from C to D of pi r of y squared dy. So instead of it being a function of x, it's a function of y. And this is the volume of revolution about the y-axis of the region x is equal to, region bounded by, I need to say. X is equal to r of y on the interval CD. Okay. We can start this problem. We have 3 minutes. Okay. So instead, we're going to revolve about the y-axis. So this says, find the volume of the solid generated by revolving the region bounded between the y-axis and the curve x equals 2 over y on the interval 1 to 4 about the y-axis. Okay, so we first have to again draw the curve. Okay, so x equals, y is equal to 1 over x. That is, looks like this. All right, so x equal to 2 over y. It's going to look similar. And we only want to go between y is 1. So we know we're going to revolve this thing about the y-axis. So this is going to give us some kind of funnel cone. And y is between 1, which is down here, and 4, which is up here. So for any value of y that I choose, I'm going to make a disk. And all I need to do is find the radius of that disk. Okay, any questions? My little coasters here. All right, this section is not a section that you decide you're going to take an L on. This section requires you to draw pictures, figure out domains and regions where they're going to be integrated from, and do different integrations. So you are going to need to practice this. Okay, please practice. All right, tomorrow I'm going to do some more of this and talk a little bit about the washer method. Okay.